We're going to start our second talk. The second talk is given by a student from the Citadel.
Kuo-Wei.
Yes. Okay. His topic is the low-rank matrix approximation and its application in image processing.
Good afternoon, everybody. My name is Kuo-Wei Yao from Citadel. Today I'm here to present my senior research. And I did this research with the professor in my math department, Dr. Chen. So for the presentation, it's going to be some basic introduction about my research, and then singular value decomposition, which is really important in my project. I'll explain it later on, and then low-rank matrix approximation, approximate the image. And then the method algorithm will be introduced. Also, we have some example here in conclusions. For introduction, before I start, I want to make it clear that every image in our research is going to be black and white, because black and white image is more simpler. It only has two-dimension matrix, sometimes simple 3 dimensions. We try to use color one, but it adds more complexity to calculate and it's going to be different method. So just consider the black and white one. So just every image we receive, if you want to turn it into a computer system, it will be transformed into a matrix form and then stored into a computer system. So, for example, we have this camera made right here. You put it in the computer systems, it will be transformed into that kind of matrix form and store it. And also, each element of this matrix represents a single pixel of that image. So our research trying to just take out the important value of this matrix and use this important data to approximate the original one. So by doing this, we can save a lot of space. We're not trying to improve the image quality. We try to use less information to approximate the original one. So we want to approximate the original image, which is formed by matrix A, by producing A sub k. A sub k, which is a simplified matrix. So how do we form A sub k? Here's some basic terminology here. R represents the rank of that matrix A, and also I is the singular values of that matrix. I'll explain later. And use I, this I will be the respective left and right singular vectors. So when we do the singular value decompositions right here, a matrix A can be actually written by this current form as 1 times use of 1 times v sub 1 transpose plus blah, 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 all the way to the last rank. So for example, if this matrix has a rank of 200, it will be 200 pairs of this one. And we want to form A sub k, which will be between the first rank to the last rank. So let's say if k equals 20, there will be the summation of the first 20 single pairs. If k equals 80, there will be the first 80s. So our question is A sub k is a good approximation compared to the original one? I don't know the vectors, because I only got 15 minutes, so I'm just trying to make this quick. So just, if we want to decompose a symmetric matrix, which is 2 by 2 or 3 by 3 square matrix, if we can find out its eigenvalue and vectors, we can actually, eventually we can decompose that symmetric matrix into 3 parts, which D will be the matrix with this diagonal of the eigenvalue, and B transpose that represent its eigenvectors. But somehow, here's some basic examples. I might just completely skip that. And also, so for the non-symmetric matrix, which is matrix formed by 2 by 3, 3 by 4, 5 by 6, non-square matrix, we will use a different way to decompose it called singular value decompositions. They are basically same way as previous as the eigenvalue vectors, but it just has 2 more steps to do it. So here's some examples. We did it twice. We have to form it into the 2 different symmetric matrices, and then we do the eigenvalue vectors, and then we combine together. That is how we find our singular value vectors. So eventually, when we do the singular value decompositions, we can decompose that non-symmetric matrix into U times D transpose, which D is also a matrix with diagonal of its singular values, and the V and the U and V transpose are its eigenvector respect to the symmetric matrix we formed previously, A times A transpose and A transpose times A. So the low-rank matrix approximation of that image. So here's on your left is an original matrix. It has rank of 253. However, if I just take the first 20 singular pairs, I take it out and then just use that to approximate that image, it gives me this kind of fuzzy picture. If I take it further, all the way up to the first 80s, which it gives me a really decent approximation compared to the original one. At your eyes, you couldn't see the difference, and I only used 31% from the original information, so which I saved almost 70%. And here's the method we use. After the singular value decomposition, we can actually rewrite the matrix A into that kind of forms, which is summations of S of I times U sub I times B sub I transpose all the way to the last rank. However, it could be equal to the summation from the first pairs all the way to the case pairs, and plus summations from the k plus 1 pairs all the way to the last one. They are the same one. So our theory is, if the second part of these formulas is really close to 0, that means we can ignore it, because even you add those back, which are a lot of information, if you add those back, it couldn't make much difference. So that's our theory. So eventually we can replace the original matrix by A sub k. And the math theories in linear algebra behind this is because if you want to minimize the difference between 2 matrices, A and B, what's the efficient way to do it? You just take the same matrix, but A sub k is just a simplified one. They are actually the same matrix, but just simplify one. So that will guarantee you have the minimized error, which will be the error of the image approximations. And this part right here is just, we will divide every singular values by its largest singular value, which it will be the first singular value. I forgot to mention before, the characteristic of the singular value it's going to be from the biggest one all the way to the last one. It's dropping. Alright, never mind. The characteristic of the singular value, it will start the biggest one, the first one, and then it will be decrease. It will never come back to get larger. It will always decrease all the way to the last rank. So that is really important because it helps us how to determine the case, how much case we want. So the way we want to do it, we divide every singular value by the first singular value, so that will guarantee no matter what kind of picture we receive, difference matrix, we all have the same standard to determine the singular value to our So here's the method. In our method, we will have two criteria called epsilon 1 and epsilon 2. Actually, epsilon 1 is kind of set up the range. We set a line here. Every singular value below this line, our computer will start do the calculations. And also, epsilon 2 is kind of the ratio effect. When the curve of the singular value it decreases, and when it going to be flat, that point, that's where we're going to cut the point. Decide the case values. So here's our two examples. Usually, in most cases, we only need epsilon 2. But however, here's some extreme case. This is actually a distribution of single value of the matrix that the image is called the chessboard, black and white with the squares. This is actually its distribution of single value. You can see from the first to the seventh single value, they are all the same. So if we only use the epsilon 2, guess what? No matter how small your criterion is, the program will always stop at the second term because they are the same, the difference are zeros. So by doing this, we will lose from the third to the seventh. These are really huge single value. We don't want to miss it. But however, in this normal case, we usually just need the epsilon 2. Just check their random ratio. If they are going to be flat, that point, that's where we want to cut it. It depends on the criterion the data we put. Epsilon 1 and epsilon 2 is decided by myself. You can make it larger or smaller. And our algorithm will be with the computers. When we receive that matrix, we will calculate its first seconds singular pairs, and then the computer will start running the third one, fourth one, fifth one, all the way till that singular value satisfies both epsilon 1 and epsilon 2 at the same time. The computer will start calculating. That's how we decide the k values. So here's a case I use in my program. So from your left is the original one. It has 253 ranks apparently. And at first of all, I set up my epsilon 1 as 10 to minus 1 and epsilon 2 as 10 to minus 2. And it gives me these kind of pictures. It stops at the rank 3, and I make it smaller. Eventually, epsilon 1 with 10 to minus 2 and epsilon 2 with 10 to minus 3. It will stop at the rank of 60. It gives me a really decent approximations. So by this case, I pretty much save over 70% storage compared to the original one. And here's the distribution of singular value. I just want to show you on the data how we cut the point. How we cut point. As you can see at the bottom of this slide, this is the last approximations. And you can see the computer stop right at rank of 60, and from 60 all the way to 253, we just ignore it because the data is really small. This is like a 10 to minus 3 right there, so it's really small. We don't want to use that. Even you put it back, it still won't make a huge difference. And here's the second case. I use Dagger is really popular singer in Taiwan, and I use the same criterions. And eventually, I only use 30.8% from the original informations. I approximate that. They are pretty much the same pictures. And these are also the distribution of single value of that. The first one, second time, third time approximation. I just want to show you where we cut the points. As you can see this picture, somebody might ask, right here is not even flat. If you want to cut it, it should be cut it right here or right here, right? But you have to say this. You also have to look up the values. 10 to minus 2 is really small. It's really small. And so our conclusion is we try to use less information from the original one to approximate that image, and hopefully we can get a good quality with less information. And a further study, I've been thinking about you approximate the color pictures, which will be more difficult. And I'm still looking at a more efficient way to estimate K. I think about if I can use less K, more accurate, to save more space, but also give me same quality of approximations. So that's my presentation. Thank you so much. And that's actually these theories that minimize about the difference between two matrices. That's where it comes from. Have any questions?
In the last two examples you showed that you have a matrix with rank 253 and you fall down to rank 60, right?
Mm-hmm.
And the last example, you have a rank 333 and you fall down to 46.
Yes.
Okay. My question is, how is that computer time consumed?
What?
Computer time consumed. How?
You mean how long does it take?
Yes.
It takes like 2 seconds.
2 seconds.
Yes. And there's a difference between, see, like this picture, even I use the same criterion, this picture sees more efficiency because I only use 30.8%. That's because different matrices, they have different characteristics. They have different distribution of singular values. Like some pictures, their first 10 singular value might be really huge, and from the 11 to the last one, it could be really small. That means we don't need that. That's where we cut. But some matrix, you might have from the first one to the 100, they're all big, and it dropped from the 100 to the last one. So the result might be varies. The K values is not all the same.
If it is
No, go ahead.
if this is called picture, what's the rank?
If it is a color picture, the rank will be more, and also there will be 3 dimensions, and it's totally different theories to decompose that matrix.
I was just going to say, this is going to have tons of applications. You know, like, I mean, Facebook would be interested in this technology.
Yes,
Once you can figure out the
but you know, there's so many ways to compress the image. So
but in medicine, there are a lot of black and white images. You know, CT scans, MRI scans, and they do more and more and more imaging, and they don't know what to do with all the data. And storing all that, it takes a lot of computer space, and so they're always looking for new ways to get creative with image, these kind of files. So it's like they have a lot of good applications.
Thank you.
Yeah, with respect to the original metrics you get from your picture, are there like any patterns? Because sometimes you might take advantage of the structure of the matrix. Say it's like triangular and stuff, like, you understand what I mean? If the matrix is say like triangular or it has a platform, sometimes you might take advantage of the programming in terms of getting the similar value decompositions and stuff like that.
Can you repeat that?
So my question is, looking at your initial picture, you come up, you get a matrix representation of it, correct? Yeah, so the question is, most often the matrix representation that we get, they have like a pattern. Because again, sometimes depending on the matrix that you have, if it has like a structure or a pattern, you can take advantage of it and it facilitates getting some values or things that you're interested in.
I guess I have answered to that question.
Yeah.
My belief is you cannot just look at the matrix, because you see that is an internal work in the computer. So, and if you are very lucky, you will have a triangular matrix, right? But only if you are lucky.
The reason I ask that, in terms of like the programming, you could do like a flow if, then.
Oh, okay, like
it makes it.
one if.
Yeah.
Okay.
It makes it easy. Then another question that I do have, with respect to, initially we talked of getting the eigenvalues and stuff like that. Now, the multiplicity of the eigenvalues, does it play any effect in terms of forward calculations?
Eigenvalues for symmetric matrix and the singular values for non-symmetric. They use the same way to decompose it, but just singular value, it just takes 2 steps to calculate it. And for this one, that's what we do by hand, but for computers, you just like see I receive this matrix and computer will do it for me, because if I do it by myself, the number will be so nasty.
Yeah, sure. Yeah, because my question was like, the eigenvalues, sometimes they do have multiplicities. Does it have any effect in terms of, further calculations or the calculations we have down the road?